Good morning friends. So now I am going to explain about the timer modes of operations. So first one, timer mode 0 operation. So the mode 0 will be selected by setting M1 and M0. They are the mode specifier bits of timer register is equal to 00. So as we know, the frequency source for the timer is crystal oscillator, that is divided by 12, so that output of the divided by 12 circuit provides a machine cycle. That machine cycles will be given as a one input to the AND gate, and another input is timer run control bit TRX, and output of the AND gate is connected to timer low register, and it is 5 bits here. See here, the pulses are going to be supplied, that is the output of AND gate, whenever the TRX is 1. Otherwise the pulses are not going to be supplied to the timer. So when the pulses are supplied to the timer low register, it is incrementing. It is keep on incrementing for every pulses. When it reaches to the maximum and it becomes 0, it provides a pulse to the timer I register, and it is here 8 bits. So here the timer low is 5 bit, means maximum value is 5 ones. In hexadecimal it is 1 FH. So with the next pulse it becomes 0 0. Then that time it provides the pulse for timer I byte register, and then it is incrementing. It is keep on incrementing. When timer I register also reaches the maximum, and with the next pulse it becomes a 0, so that the pulse will be provided. With that pulse it sets timer flag 1. Then it so that means to say timer flag will be set to I whenever the maximum count value is 1 FFH becomes a 0, because so totally together timer low byte is 5 bits, timer I bytes is 8 bits, together 13 bits. 13 bit means it counts from 13 zeros to 13 ones. 13 ones in hexadecimal we write 1 triple FH, and whenever timer flag set, interrupt will be occurred. This is the operation of timer mode 0. Next we'll see timer mode 1 operation. It is very similar to timer mode 0 operation, only the difference is the mode specifier bit values is 0 1, and in the previous mode 0 operation TLX was 5 bits, here TLX is 8 bits. So the maximum count is 4 FH, and when it becomes 0, timer flag will be set to 1. When it's set to 1, the timer 1 interrupt will be occurred. Timer 1 interrupt will be occurred. So next we'll see mode 2 operation. We also call it as auto reload mode. Why we call it as auto reload mode? Means the initial value will be loaded automatically. So this mode will be selected by setting the mode specifier bits 10 in T mode register, and the operation is similar. The crystal oscillator provides the pulses, and output of AND gate is connected to TLX. It is also 8 bit. So initial value will be loaded into timer I register, and that copy of the value will be copied into TLX timer low register. Whenever the pulses are supplied, TLX is keep on incrementing. Whenever it reaches maximum, the maximum value is when TFX goes I, when FF becomes a 0, that time the timer flag will be set to 1, and it generates timer 2 interrupt. It generates timer 2 interrupt. Meanwhile, it gives the instruction to THX to copy the initial value into TLX, and again it repeats. So here no need to load the initial value again and again. This is the advantage of mode 2 compared to the other modes. Hence this mode is frequently used in baud generation applications for serial communication. So we'll see mode 3 operation. It is also called as split timer mode, and this mode will be selected when M1 and M0 is 1 in T-mode register. So we call it as split timer mode, means here only timer 0 is used, timer 1 is not used, and the timer 0 is splitted into two 8-bit timers, TL0 and TH0. So for TL0 we use control bits of timer 0. See, timer TR0 is used to make it is on or off, and TL0 is the timer. Whenever it reaches the maximum, timer flag 0 will be set to 1 and the corresponding interrupt will be occurred. And this can be used as a timer or as a counter. And another one, TH0. For that TH0 we use control and flag bits of timer 1. As you know, TR1 and TF1 is the control and flag bits of timer 1, no? So this is used to make it is on or off, and TH0 used as a separate 8-bit timer. Whenever it reaches maximum value, the timer corresponding timer flag will be occur, then the interrupt will be generated. So this can be used as only timer. The previous one, TL0 in mode 3 can be used as a timer bar counter, but TH0 in mode 3 can be used as only the timers. So these are the different modes of operations of a timer. Next we'll see programming of timer. That means to say, first we'll see the steps to be followed to write the program. First step is initialize T-mode register to indicate which timer is used and in which mode it is used. That means you need to load the value to T-mode register. So T-mode will be equal to 01 to select timer 0 in mode 1. And similarly it should be equal to, the value will be equal to 10 to select timer 1 in mode 1, and T-mode value will be 02 to select timer 0 mode 2, and T-mode will be equal to 20 to select timer 1 in mode 2. So this is the first step to initialize timer mode register to indicate which timer is used and in which mode is used. The next step is to load the timer low register and timer high register with the initial counts. Once it is loaded, the next step is to start the timer using an instruction set bit TRX. Here X can be, remember, X can be either 0 or 1. Then keep monitoring the timer flag with the instruction target : jump no bit. JNB means jump no bit. If bit is not 0, go to the target. So it will be keep on there until TFX becomes 0. Then after that, stop the timer using an instruction clear TRX. Then clear the timer flag for the next round. Then go back to the step 2 to reload TH and TL value again for mode 0 or mode 1. But you need to go back to step 3 for mode 2, because it is, since it is an auto reload, for mode 2 go back to step 2. So with this steps, now we'll write one program. See the question: write an 8051 ALP assembly language program to generate a square wave of 1 kHz on P2.1 using timer 1 in mode 1 operation. That means it is required to write a program which generate a square wave on port pin P2.1 and assume crystal frequency as 12 megahertz and show the delay calculation. So this is the question. So first we need to understand it is required to generate a square wave of 1 kilohertz on P2.1. For that purpose we should use timer 1 in mode 1 to generate the delay between the on period and off period. So the crystal frequency is 12 megahertz. Now let's see the solution. It is given that crystal frequency, that is XTAL frequency, is 12 megahertz. As you know, this frequency will be divided by 12, then that will be given to the timer. So timer frequency is 1 megahertz. 12 megahertz divided by 12, it is equal to 1 megahertz. When the timer frequency is 1 megahertz, the corresponding timer period 1 over f, 1 divided by 1 megahertz, that is 1 microsecond is the timer period. So next, it is required to generate a 1 kilohertz frequency square wave, no? So the time period is, for 1 kilohertz frequency, time period is 1 millisecond. Since it is a square wave, duty cycle is 50%. So T on is 0.5 millisecond and T off is 0.5 millisecond. Next, it is very important to understand how to generate delay of 5 milliseconds. See here, one timer period is 1 microsecond. So then to provide a time of 0.5 millisecond, how many machine cycles are involved? We need to calculate. To provide 0.5 millisecond delay, how many machine cycles supposed to be involved? So for that we need to calculate count value. The required delay is 0.5 millisecond and that is divided by time period of a machine cycle, so that is equal to 500. Now with this value we need to find out the initial value to be loaded into timer low and timer high register. So in mode 1 is a 16-bit timer, no? The maximum value is 4FH, that is 65,535 plus 1. So 65,536. Here y plus 1 means the initial value starts from a 0. So the total number of count is 65,536 minus 500 required count. So that is equal to 65,036. It's supposed to be an initial value. So timer counts from this initial value. Whenever the one machine cycle occurs, it counts up 65,037. Next, for the next machine cycle, 65,037, 38, 39, like that. So this is the decimal value and the equivalent hexadecimal value is FE0CH. Then timer high register value is FE and timer low register value is 0CH. So this is the procedure to calculate the initial value to be loaded into timer register for the required delay. So with this knowledge, now we'll write a program. So while writing the program, we should follow the steps which we discussed in the previous slides. As you know, the very first instruction is ORG00H, since whenever we reset the microcontroller, PC will be loaded with a 0. And the first step, we should initialize timeout register. No, here the question is to ask, a question is asked using timer 1 in mode 1. So the value to be loaded is 10H. So with this, it selects, this is the comment, it selects timer 1 in mode 1. After that, the second step is to load the initial values. As we calculated, initial value for timer low register is 0CH. It is the initial value for timer low, and for timer high the initial value is FEH. Here FEH is preceded with the 0. It is just to avoid the confusion. F is not an alphabet, it is an hexadecimal digit. So this is the initial value for TH1. So once we loaded the initial value, so the next step is to start the timer, right? Yeah, start the timer. So before that, complement the pin P2.1. So this is the pin where we need to generate the square wave. Complements the value. Suppose if the value is 0, it becomes 1. If it is 1, it becomes a 0. Make the pin either 0 or 1. So suppose assume it is a 0, it becomes 1. Then provide a delay of 0.5 millisecond. Then make it is 0. Provide the delay of 0.5 milliseconds. So for the delay, we use subroutine concept. We call delay. A call delay. A call means absolute call. Absolute call in the sense, here the program memory is divided into 2k pages. 2k pages. The instruction which calls the subroutine as well as the subroutine supposed to be within the same 2k pages. So whenever this instruction executes, it copies the return address in the sense address of the next instruction to be executed, that is sjump repeat. Address of this instruction will be copied into a stack. Okay, and this is the main program. So go to sjump repeat to repeat forever. Otherwise, if it is required to generate so and so the number of pulses, here we use the instruction decrement jump not 0 back. There the value will be loaded as many pulses are unneeded to the any register. Here repeat goes to load initial value again. Okay na? Yeah. Now we'll write delay routine. See, initial value is loaded. First step, timer register is initialized, mode register is initialized, and initial value is loaded. Now we call delay. So here the first instruction of the delay subroutine should be the next step, that is start timer with the instruction just set bit TR1. Start timer 1. Then the next step is to keep monitoring the timer flag using an instruction JNB TF1 again. It is keep on monitoring the timer flag 1 until it is set to 1. Whenever it is set to 1, it executes next instruction. So the next instruction, as we know, the next step is to stop the timer. First clear the timer flag and then stop the timer with the instruction clearly. So these can be interchanged. No need to worry. First you can stop the timer, then you can clear the timer flag. No need to worry about it. And then return. So whenever the return instruction executes, it retrieves the return address which was loaded into the stack. It retrieves into a program counter. Then execution starts from the next instruction of the call. Here the next instruction of the call is jump repeat. So it goes to the repeat. Again it reloads the value, complements the P2.1, calls the delay. It comes and provides the 0.5 millisecond delay. Again it goes back to the next instruction. The next instruction is just jump repeat. It goes to initialize. So it is keep on repeating. So this is the program which generates 1 kilohertz frequency on P2.1. So we'll discuss some more programs.